Math 150, Section 1, lecture probably 13. What we're going to do today is do directional derivative. We'll do some consequences of various formulas. We'll do some prep work for later in the semester when we get to the Taylor series and stuff like that. We'll do trigonometry in a minute. And then if there are other things you'd like to see, let me know. This class is a little bit light in material. This is deliberate, so we have a chance to really go over things we've done up until now. The first midterm is probably going to be, I think, next Wednesday, trying to give you plenty of time to prepare for the material. All right, so directional derivatives. So in some sense, we've really done directional derivatives already. There's not that much more to do, but to just formalize some of the concepts we've seen. So we can fix a vector v. And we can fix a function f. And we can look at the limit as h goes to 0 of f of x plus hv minus f of x divided by h. And I'm putting an arrow over h to remind ourselves that we're evaluating f at a vector, maybe x1 through xn. And I'm fixing a direction, and we're moving in that direction. What would you like to assume about the vector v?
It has unit length.
So one thing is probably it has unit length. I definitely don't want it to have 0 length, because if it has 0 length, the numerator is always going to be 0. It's probably not a bad idea to assume it has length 1. If it doesn't have length 1, all you're essentially doing is you're rescaling it. If you have length 2, if you just put a 2h down here, you can essentially incorporate that length. So we often assume that the length of v equals 1. And again, I like to be a little bit of an overkill and use the double vertical lines to emphasize that I'm talking about a vector. So this is a perfectly good object to define. We have seen special cases of the directional derivative before. Where have we seen special cases? So what's a special case of the directional derivative? Special choice of v. So what derivatives have we seen so far in multi? Partial derivatives. So this is so partial derivatives are special cases. So we'll just take, in that maybe v to be a unit vector in the EI direction. So all we're doing now is saying, let's allow ourselves to travel in any direction. And so if I wanted to compute the directional derivative, I could use this formula. One of the big themes of Calc 1 is to get away from the definition, right? If you want to calculate the derivative of x to the 1701, have any of you ever calculated the derivative of x to the 1701? Right. You are not going to use the binomial theorem and expand out x to the 1701. You're going to use the power law, which you have stated and proved. So we want a better formula for computation. Let's let c of t be x of t, y of t. So what I'm going to do is I'm going to do the argument in just one dimension. I'm sorry, in 2 dimensions. The argument in general proceeds similarly. I'm getting a little bit of a glare, so I'm going to just try adjusting the lights a little bit. All right, so let's try a curve c of t. I can now look at a function a of t is f of c of t. So when we're doing the chain rule, instead of c of t, what letter did I use instead of c? G. I use G for a general function. Here I'm using C. So you always want to ask, why am I using C? Well, today's my son's birthday. His name is Cam. I'm doing this to honor him. I'm not honoring my son right now. Later, that will happen. Any idea why I'm using the letter C? You want notation that's good. So here's my path. C of t is x of t, y of t. This is a curve. I have some curve in space, and at time t, I'm at the point x of t, y of t. And so if I look at this, if I look at it on the left-hand side, this is just a function of t. And I can calculate a prime of t. Right? And on the right-hand side, I can use the chain rule. It's going to be df dx at the point c of t. Then it's going to be dx dt at the point t, plus df dy at the point c of t, times dy dt at the point t. So this is a little bit of an overkill writing it out like this, but so now if you look at what this is, dx dt, that's just x prime. And dy dt, that's just y prime. So I actually have my function df dx at c of t, x prime of t, plus df dy at c of t times y prime of t. So let's now choose the following. At t equals 0, say we're at the point x naught, y naught. And tangent direction is going to be v, which will be x prime of 0, y prime of 0. So going back to my curve, here's my point x naught, y naught. And at that instant, the curve is moving in that direction. So this is a way to calculate the directional derivative. I'm moving instantaneously in that direction. So now, if I just simplify the algebra of what I have, we will get a prime of t is going to be df dx at the point x naught, y naught times v1 plus df dx, or df dy, at the point x naught, y naught, v2, where our vector v, I'm just writing as v1, v2. Well, this is the same as the gradient of f at the point x naught, y naught, dotted with the vector v. Because remember, when you have a dot product, it's first component times first component, plus second component times second component, plus third component times third component, and so on and so on and so on. And this can hopefully begin to look friendlier to you. We know the special directions. We know how to take the partial with respect to x, the partial with respect to y. And now we're relating the directional derivative in any direction to our knowledge of the partial derivatives. So it's telling us that if we can just understand what's going on along the coordinate axes, not surprisingly, we know a way of piecing it together to get what's going on in any other direction. So all you really need to do is go through and see that this really is the same. So imagine you take the straight line curve. So we're now taking, say, the curve x of t, y of t equals x naught plus v1, y naught plus v2. T. So this is just x naught plus t v1. This is y naught plus t v2, or this is the point x naught, y naught plus tv. And so now when we're trying to calculate the derivative, you can see that this is really the same as the definition of the directional derivative. It's just computationally, this is a much better formula to use. And now we can talk about how is the function changing in a certain direction. And this, in fact, even gives us a way to compute it. Take any curve going through the point you care about, whose tangent at that point is the direction you care about. Then if you compute this, you will get the directional derivative. They have assured us that we will be done with the road construction in the very near future. All right. Any questions about calculating the directional derivative? So with any chain rule problem, it's always a question of which way is best. If I give you the direction v, and you know the partials, this is a really good formula to use. If this is a hard derivative to take, it might be easy if you can parameterize a curve, plug it in, get a function of one variable, and just take the derivative directly. So let's think back about where we've used partial derivatives, where we've used these. One of the biggest applications was trying to optimize functions. Where is something largest? Where is something smallest? And we made the argument before that, well, for a function to have a maximum, if I move in the y direction either way, I can't be getting larger, right? So what would the partial derivative with respect to y have to be? If I want to be a maximum, it would have to be 0. And similarly, if I move with respect to x, what would the partial derivative with respect to x have to be if I want a maximum? Also 0. And then we said, well, that now gives us a necessary condition. So if we want to find candidates, our only candidates are going to be those points where df dx is 0 and df dy equals 0. Another way of looking at this is, well, let's just consider moving in any direction, right? No matter what direction I move, if I'm at a maximum, my function shouldn't be getting larger. So the directional derivative in any direction we take should be 0. Well, if you look at this formula now, the directional derivative in the direction of v, where v is the unit vector, is the following. If the gradient is not 0, what direction should I choose v to be in order for this quantity to be non-zero? So if the gradient is non-zero, what direction should I choose v to be so that this dot product is not 0? Yes? Well, if it's perpendicular to this direction, what would the dot product be? What's the dot product of two perpendicular vectors? So if we take two perpendicular vectors, let's take the vector 1, negative 1, which is coming down here, and the vector 1, 1. So they are perpendicular to each other, and the dot product. So if the dot product is 0, they're perpendicular to each other. Yeah, so if we take the vector v to be in the same direction as the gradient, then this dot product will be positive. So in order for us to have a maximum, the only way this dot product can be 0 for all directions is if the gradient is 0. If there's even one direction where the gradient is not 0, move in that direction. And in fact, that will be the direction of maximum change. That'll be the direction where you're increasing the fastest. So this is a really good thing to isolate. So directional derivative increases fastest when v is in the direction of the gradient of f. What direction do you think we should go in order for it to decrease the fastest? So if we go in the direction of the gradient of f, it's increasing the fastest. Which direction should we go opposite? So it decreases fastest when v is in the direction of negative grad f. So the gradient of f is pointing the direction of the maximum change. There's a really nice interpretation of the gradient of f. So if you walk in the direction of the gradient of f, you're increasing as fast as possible. If you're walking in the opposite direction, you're decreasing as fast as possible. What do you think would happen if you walk perpendicular to the gradient of f? I'm sorry? Your function is not changing. So this is where we get the tangent plane, or the tangent hyperplane. The gradient of f is pointing in the direction of maximum change. So if you want to look at all values of f that have this, all inputs that have the same output onto f, the instantaneous tangent plane, the tangent plane at that point, is going to be the plane whose normal is the gradient of f. So gradient of f points normal to the surface. And we're going to see great applications of this when we get to Lagrange multipliers. Okay. So whenever possible, it's wonderful when we can get geometric interpretations for what we're doing. And if you think about it, we're reducing everything to just being able to compute derivatives in the coordinate axes. And now we've pieced that together, and that's the gradient of f. That's a really nice derivative. And that derivative is telling us an enormous wealth of information. When we want our maxima and minima, we now know the gradient of f has to vanish. We argued this before, but we can see it again by saying, if the gradient of f is not 0, well then all I need to do is just choose to move in that direction. And if I move in that direction, then my function will be increasing. If I move in the opposite direction, it will be decreasing. Any questions about the gradient of f? So if I want you to calculate directional derivatives, all you have to do is use this formula. You just calculate the regular gradient, and you just do a dot product. So it's just taking together two pieces we know. And then when we get to Lagrange multipliers, we'll then see some real applications of this. Okay, I'm just double checking in terms of what the students wanted to see. There was one request. Okay. Okay. So I want to make just one brief point about derivatives. I'm not going to go into too much detail on this. There are two big theorems that you can mention at this stage in your career, but you really don't see the details until real analysis. It's the inverse and the implicit function theorem. The book says a few things about this. The main idea is, if I have x as a function of y, when can I write y as a function of x? So the important thing to remember is there is a difference between being a function and being a relation. For a relation, you can associate multiple outputs to the same input. For a function, each input has one output. A good example might be sports teams you like, colleges you hate. Right? You can have multiple answers for stuff like this. You can like more than one team. Which school do you go to? Pretty sure this will be singly valued. You're not going to go to college at the same time at multiple schools. Or at least, if we further localize to at 9:19 a.m., that should then be enough to make it singly valued. So this is the question. If y is a function of x, when is x a function of y? So for example, let's say f of x equals x squared equals y. This is, about my level of artistic talent. If you give me an x, is y uniquely determined? If I tell you x, do you know what y is? If I tell you x equals -5, well, y is just -5 squared. This is a unique value of y. If I tell you x equals 3, y is just 9. For every value of x, there's a unique y. And it's often called the vertical line test. If I take a value of x and I go straight up, it's going to hit the curve once and only once. So this is the vertical line test. So you give me an x, there's one and only one y. What about the inverse? If I give you a y, is there only one x? No. And so there, when we do the horizontal, if I give you a value of y, there are two possible x's. So vertical line test passes, horizontal line test, it fails. So this is not a good situation for us. There is not an inverse function defined on all the reals to my squaring function. But there is if I restrict myself to just say positive x. We're okay if we say y equals x squared for x greater than or equal to 0. So if we just restrict ourselves to x greater than or equal to 0, now if we look at the plot, it's going to look like this. And now an inverse exists. And so one of the questions is, when can you tell if a function is invertible? So the inverse function theorem is basically telling you when you can have a situation like this. And a really good condition is you're okay if f prime of x does not equal 0, at least locally. So as long as your first derivative is not 0, then your function is either increasing or decreasing. And if your function is increasing or decreasing, then for a short window, there will be a one-to-one map. And you can then say, okay, if you give me a y, I can then give you an x. Long term, it may fail, but over a short period of time, and the reason is, in a short period of time, if the first derivative is not 0, then essentially your function is a straight line. It's a straight line over a very small period of time. And a straight line is invertible. If ax plus by equals c, I can write x in terms of y, I can write y in terms of x. The problem is, over a longer period of time, you might then go all the way down to a point where the first derivative is 0. Just because the first derivative is 0, does that mean the function is not invertible? No, we've got the function y equals x cubed. So if you look at the function y equals x cubed, the first derivative vanishes at x equals 0, but this is always invertible. You just have x equals the cube root of y. So there are ways to tell when a function is invertible or not. I want to talk a little bit about invertible functions, just because most of you probably have not seen how to calculate inverse trig functions. It's a nice application of the chain rule. So for instance, how many of you have seen the derivative of arctangent? Oh, good, okay. How many of you could derive the derivative of arctangent right now? Okay. How many of you have seen the derivative of the exponential and the logarithmic functions? And why we use base e? So there are almost always gaps because people come from different schools with an emphasis on different things. So what I want to try to do in the semester is try to concentrate on a couple of things that I have just noticed over the years, either gaps or things that were not covered in great detail. So this is one of the best applications of the chain rule. Inverse functions and the chain rule. So let's let a of x be f of g of x. And let's assume we are in the very special case where f of g of x is x. This is also known as the identity map. Sometimes we'll write as ID for identity. It takes as input x and gives back x. This is one of the easiest functions to understand. What does it do to the input? Nothing. Right? This is almost like the Seinfeld of functions. Right? What would be the derivative of a of x? 1. There's two ways to calculate the derivative. So one is, well, a prime of x by the chain rule, it's f prime of g of x times g prime of x, and it's also just 1. So we can use this to solve for g prime in terms of f prime. We get g prime of x is 1 divided by f prime at g of x when f of g of x equals 1. So this is a terrific result. If f and g are inverse functions, if I know the derivative of f, I now know the derivative of g. Okay? Let's do some examples. Again, my philosophy is to work you hard in the start of the semester and then ease up as the semester ends. I know a lot of my colleagues in other departments sometimes have the end of the semester very busy. So we will be getting to Taylor series of great detail later in the semester. I'm going to just start with a little bit right now. Let's look at the exponential function. E to the x equals exponential of x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus yada 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 equals the sum and goes from 0 to infinity of x to the n over n factorial. This is one of the most important functions in mathematics. What's the derivative of the exponential function? E to the x. Have you seen a proof of this? Yes.
It kind of makes sense just looking at that.
Okay.
Because the derivative of 1 is just going to be 0, and then the derivative of x is going to be 1.
So if we take the derivative, 1 goes to 0, the derivative of x goes to 1, x squared over 2 factorial becomes 2x over 2 factorial. We'll have 3x squared over 3 factorial plus 4x cubed over 4 factorial. And that's going to be 1 plus x squared over 2 factorial, because the 3 cancels with the 3, plus x cubed over 3 factorial. And this is just what? E to the x. Is this a proof? Yes.
Probably not really, but it's very easy to make the actual proof by just looking at what you're taking the sum of, because the derivative of each term,
right,
looking at the sum, is just going to be nx to the n minus 1 over n factorial, which is just...
So I agree that you will get the nth term becomes x to the n minus 1 over n minus 1 factorial. Is this a proof, or is there something I'm glossing over here? And given that I'm pausing, I'm probably glossing over something. I'm doing something that's slightly illegal. I'm saying the derivative of an infinite sum is the infinite sum of the derivatives. You never proved that. It's not always the case. I can make this rigorous, but it's something you haven't really seen. Technically, I think all you've proven in high school or calculus class here is the derivative of a sum of 2 terms is the sum of the 2 derivatives. I don't know if you've even proved the derivative of a sum of 3 terms or 4 terms or 5 terms. Let me quickly show you that any finite sum will work. Actually, well, let me keep this stuff on the board for a little bit, so I'll move over here. So this is one of my favorite proof methods. Proof by either grouping or by parentheses. Let's calculate the derivative of f plus g plus h. We're going to calculate the derivative of this. And let's assume we know the derivative of a sum is the sum of the derivatives. So this is, I can group f and g together and add h. So I'm grouping f and g together as one function. Now I have a sum of 2 terms. By what we know, the derivative of the sum is the sum of the derivatives. So this is just going to be f of x plus g of x prime plus h prime of x. Now what do I do? So I started with the sum of 3 terms. I grouped 2 of them together, and now I'm in a situation where I'm just using the derivative of a sum of two terms is the sum of two derivatives. So I now have, it's the derivative of f plus g plus the derivative of h. Now what do I use to calculate the derivative of f plus g? So what would I use? I'm sorry? The same rule. So now this is just f prime of x plus g prime of x plus h prime of x. And because addition is commutative, now I can just drop all the parentheses. It's just f prime of x plus g prime of x plus h prime of x. And this proves the derivative of a sum of three terms is the sum of the three derivatives. I could do the sum of four terms, the sum of five terms. Any finite sum I can do like this. But I can't do an infinite sum. And for an infinite sum, I have to be very careful and I have to worry about convergence. Because n factorial is growing so rapidly, you can make this rigorous. And we haven't done so yet. So for an introduction, absolutely fine to say, let's just say the derivative of an infinite sum is the infinite sum of the derivatives, and let's move on. And so if we were to do that, then that would justify our thought that the derivative of e to the x is just e to the x. Yes?
So with this method,
Would mimic what?
So
Okay, so for Newton's method, we are hopefully generating a sequence of points that is going to converge to a root. What you could do is you could look at approximations to e to the x. And the hope would be that as you take more and more terms, it converges to e to the x. So in that sense, yes, it is similar to Newton's method. When you see e to the x, what is e squared times e cubed? E squared times e cubed is what? E to the fifth. We haven't proven that. Technically, the way we've defined e to the x is it's an infinite sum. The notation would suck if this was not true. But technically, we have not proven that. If I want to give you e to the x times e to the y, it's the sum of x to the n over n factorial times the sum of y to the m over n factorial, and then after some algebra, you show it's the same as the sum of x plus y to the k over k factorial. This can be shown using the binomial theorem. As a nice exercise, try to prove that. Technically, this is what we mean by e to the x. We mean this infinite sum. This is what we mean by e to the y. E is a strange number. It's not a natural number. It's not a rational number. It is a strange number. It's defined by this infinite sum. If it didn't have this property, this definition would suck. We've given you cosecant as 1 over sine. We don't have a great track record. So you do have to be careful. Right? It turns out that this is true. And when we get to sums later in the semester, there's a good chance I will prove why this is true. All right. Let's do some applications of our inverse relation. So we showed that if we have two inverse functions, the derivative of g is 1 over f prime at g of x. How many of you proved what the derivative of the natural log is? What's the derivative of natural log of x? I'm sorry? Well, no, I'm not giving you natural log of u of x. I'm giving you just natural log of x. What is the derivative of natural log of x? 1 over x. How many of you proved that? How did you prove it?
I actually proved it using that method.
Using this method?
I knew that, yeah.
Okay. Anybody else remember proof of the derivative of the natural log? So we want to find two functions that are inverses. So consider the exponential of the natural log of x, or e to the natural log of x. So what am I doing? The natural log of x means how many powers of e do I need to get x? So I raise e by the number of powers of x I need to get x. This is basically proof by vocabulary. If you raise e by the number of powers of e I need to get x, what do you get? X. So now we're in the situation where we can use our result. So this is our function f. This is our function g. So g prime of x, which is the derivative of the natural log of x, is just 1 over f prime at g of x. But what's the derivative of the exponential function? It's the exponential function. So I just get the exponential function at g of x, which is the natural log of x, which is just 1 over x. And so this is the proof that the derivative of the natural log is 1 over x. If you wanted to take the derivative in a base other than e, you can do this, but then you have to remember there's a log b that floats around. I guess just for completeness, just so you have seen it at least once in your life, I will state that result. The change of basis formula. The log of x base b is the log of x base c over the log of b base c. This is a great formula. It means if I understand logarithms in one base, I understand logarithms in every base. In particular, if you take c equals e, you get the log of x base b is the natural log of x divided by the natural log of b. And so now, if you take the derivative of the log of x base b, you get 1 over x natural log of b by the constant rule. No need to use the quotient rule here. This is just 1 over log b times the natural log of x. As an exercise, I'll let you figure out what would be the derivative of b to the x. There's going to be a natural log of b that comes out there as well. You should make sure you can do the algebra like that. If you're having trouble, let me know. But you always want to reduce things to base e because the results are nice base e. The derivative of the natural log is just 1 over x. You don't have to worry about where's this factor. In the old days, this was a far more valuable formula because people used to compute tables of logarithms. And what this tells you is you only need one table. How many of you have taken a stats class or seen the central limit theorem or z-tests? You only need to calculate the z-test for a standard normal. Because you can always normalize or standardize your variable, and now you just need one table in the back of the book. You don't have to have one for every single normal distribution. It's incredible how valuable formulas like this are. Now, in the 21st century, the computer can do this adjustment for you automatically, but it's still nice to be able to do this. So what we're seeing is we're seeing a lot of powers of the chain rule. And this is just a one-dimensional chain rule, right? But it gives us this great way to get inverse functions. So we've just done the derivative of the natural log. Let's do a more involved example. Let's do arctangent. So if I want to do arctangent, I have to think of two functions. The inside one has to involve arctangent. And I need to choose an outside function such that when I apply that to arctangent, I get back x. What should the outside function be? Tangent. Take the tangent of the angle whose tangent is x. What do you get back? X. So this tells us that the derivative of arctangent is 1 over the derivative of tangent at arctangent of x. All right, who remembers the derivative of tangent? Yes.
Secant squared of x.
Secant squared. So if you forget that tangent is sine over cosine, what would we use to take the derivative of sine over cosine? Product rule of quotient rule. So when the dust settles, you'll get it's 1 over cosine squared, which is secant squared. So we get that this is equal to 1 over so tangent is going to be secant squared, right? So we have 1 over cosine squared of arctangent of x, or just cosine squared of arctangent of x. Right? So this is the derivative of arctangent. Does the cosine squared of arctangent of x look nice to you? No. Let's draw the triangle. Here's a theta. I want to draw a theta. I want to draw a triangle with an angle, and I want the tangent to be x. So I get to choose my two sides. Let's choose this side to have length x, and this side to have length 1. Tangent is opposite over adjacent. So this triangle has an angle whose tangent is x. What would be the length of the hypotenuse? Square root of 1 plus x squared. So for this triangle, the cosine of theta is 1 over the square root of 1 plus x squared. And what is theta? Theta is the arctangent of x. It's the angle whose tangent is x. So now if I put the pieces together, cosine squared of arctangent of x, I can simplify that. The cosine of the angle whose tangent is x is 1 over the square root of 1 plus x squared. So this is just 1 over 1 plus x squared. That's much nicer than taking the square of the cosine of the arctangent of x. So what I really like about this problem is it highlights how you can reduce the complexity of something by doing some algebra. And this is one of the hardest things to do, is to see these different simplifications. Draw pictures. Sometimes it's hard to figure out how do you want to label things. Normally, when you draw a triangle, you'd make the hypotenuse 1. But for this problem, I'm telling you, I've got a problem where the angle has a tangent of x. What's the easiest way to draw a triangle that's right with a tangent of x? X and 1. Okay. Any questions on inverse functions and the chain rule and applications to finding these derivatives? All right, so we've got 6 minutes left. I can teach you all of trigonometry in 1 minute. We're golden. All right? So because we have so much time, we're going to do it casually. All right? I'm going to start off with some of the very painful trig rules. How many of you remember your angle addition formulas from trig? I can play Simon & Garfunkel's The Sound of Silence. All right, I'm going to teach you a way so that you will never, ever, ever forget your trig formulas again. All right, so we have the sine of x plus y is sine x cosine y plus cosine x sine y. And then we have cosine of x plus y is cosine x cosine y minus sine x sine y. And here is one way to do the proof. I'm not going to do the proof. You don't want to see me do the proof this way. Let's assume x and y are small. Here's my angle x, and I'll go out my angle y. So this line coming down, this length would be the sine of x plus y. I can make another right triangle by coming down like this. I can go a dot down here, and I can also have a right triangle coming down like this. I can figure out what the length of this line is. That's going to just be, if this is 1, and this is y, this length would be the sine of y. So this whole length here would be the cosine of y. And then to come down to here, this would be cosine y cosine x. And this length here would be cosine y sine of x. And then all I would have to do is figure out what this length is. Well, if this is sine of y, now you need to start play right triangle games, and you figure out that what this angle here is probably going to be maybe like an x up there because of parallel lines. If this is x here, that would be x over here. So this over here, this length would be is that going to be x? No, this would be x over here. This would be 90 minus x, so this would be x over there. So this length over here would now be this length sine of y times the cosine of x. So this piece would be sine y cosine x. That gets me down to here. Then I shift over, and this piece is cosine y sine of x. And that would get me my first piece. That would give me this angle. Okay? That works if the angles are small, and then you can play games if the angles are larger. How many of you vaguely remember something like this in a trig class? All right. I'm going to show you how to get all of this now from the exponential function. So I is the square root of -1. E to the I theta is cosine theta plus I sine theta. This is often attributed to Euler. Beautiful, beautiful fact. And if you want to think about what's going on, here's my angle theta, here's my point cosine theta, sine theta. And what we are often doing in the complex plane is this is the x direction, this is the y direction. And so I'm representing the point as cosine x plus I sine y. Think of I as a vector. Right? The way you would prove this is we know e to the z is 1 plus z plus z squared over 2 factorial plus z cubed over 3 factorial plus at the dot. You then show cosine of z is 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus at the dot. You show sine of z is z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus at the dot. And then you just show that e to the ix will be cosine x plus I sine of x. I is the square root of -1, so whenever I have something to an even power, the -1 is going to be either 1 or the I is going to be either 1 or -1. When I have it to an odd power, I'm going to get either I or minus I. So all of the odd terms will have an I in front of them, all the even terms will be real, and you just collect the dust settles, you get this. So this is a precursor to Taylor series. We're going to just accept this for now, and I'm going to show you how to get all of trig immediately. So it's going to be a race against the clock. All right. So x and e to the minus ix is e to the what? We're going to go fast, guys. Come on. Is what? E to the 0, which is 1. This is cosine x plus I sine x times cosine x minus I sine x equals 1. And what I'm doing here is, if I put in a negative sign, I get cosine negative theta. Cosine of negative theta is the same as cosine theta, plus I sine of negative theta. The sine of negative theta is just minus sine theta. This is just cosine squared x minus I squared sine squared of x equals 1. Ah, but what's I squared? -1. So this is just cosine squared x plus sine squared x equals 1. Aha! There's basically the Pythagorean theorem. All right? Let's do the angle addition formulas. We can erase the picture monstrosity. And we end with the following. E to the ix times e to the iy is e to the I x plus y. So over here we get cosine x plus I sine x times cosine y plus I sine y equals cosine x plus y plus I sine of x plus y. I feel like I'm back in the chain rule. I'm just writing. Let's multiply out. You get cosine times cosine, I sine cosine, I cosine sine, minus 1 sine sine. So we'll put the real numbers together and the imaginary numbers together. So we get cosine x, cosine y, minus, because the I is reinforced, sine x, sine y, that's the real part, plus I times sine x, cosine y, plus cosine x, sine of y. Well, the only way these can be equal is the real part equals the real part, the imaginary part equals the imaginary part. There's your angle addition formulas. If you want to find the formula for the double angle formula for x equals y, take x equals y. If you want to find half-angle formulas, triple-angle formulas. And I feel like somebody on the Home Shopping Network. You can keep getting all these different things from these relations. Incredibly powerful. This is a good place to stop.